Imagine a machine that can look back in time to the birth of the first stars and galaxies. Now consider the thought-provoking possibility of time travel, changing the past or seeing the future. These seemingly fantastic ideas form the backbone of humanity's quest to understand the universe. At the heart of this research is the James Webb Space Telescope, JWST, a technological marvel poised to reveal the mysteries of space. Furthermore, the concept of time travel, often confined to science fiction, fascinates and challenges our scientific and philosophical understanding. This study explores how JWST's groundbreaking features intersect with intriguing theories about time travel, creating a story that connects the advancement of technology with the limits of our imagination. The James Webb Space Telescope, or Webb, is the culmination of decades of scientific innovation and international collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Launching in 2021, Webb offers a design that surpasses its predecessor, the Hubble Space Telescope, in both scale and capabilities. The 6.5-meter main mirror, made of 18 hexagonal gold-plated beryllium segments, is specially designed to capture infrared light. This trait allows him to see through cosmic dust and reveal the universe's most hidden secrets. The telescope's science suite includes a near-infrared camera, a near-infrared spectrograph, NIR-SPEC, a mid-infrared instrument, MIRI, and a fine steering sensor/near-infrared camera and spitless spectrograph, FGS/NIRIS. All these instruments will play an important role in Webb's mission to observe the formation of stars and galaxies, analyze the atmospheres of distant exoplanets, and possibly find signs of life outside our solar system. Webb's mission is ambitious. One of its main goals is to study the earliest light in the universe, emitted by the first stars and galaxies that formed more than 13.5 billion years ago. By capturing this ancient light, Webb aims to provide unprecedented insights into the processes that shaped the cosmos. In addition, Webb studies the formation and evolution of stars and planetary systems. Its infrared vision can penetrate the dense clouds of gas and dust where stars are born, providing unprecedented views of these nurseries of celestial life. Additionally, by analyzing the light passing through the atmospheres of exoplanets, Webb is looking for chemical signatures that could indicate the existence of life, which could answer one of humanity's most profound questions. Are we alone in the universe? Time travel has long captured the human imagination and figures prominently in literature, film, and scientific thought. At the heart of time travel theories are pioneering ideas proposed by Albert Einstein. According to his general relativity, space and time are intertwined in a four-dimensional continuum known as spacetime. Massive objects like stars and black holes distort spacetime, affecting the motion of other objects and the passage of time itself. One of the central effects of general relativity is time dilation, the phenomenon where time passes differently for moving objects or strong gravitational fields than for objects in different reference frames. This was experimentally confirmed by precise atomic clocks and spaceships, showing that time is not as absolute as previously thought. General relativity also offers the tantalizing possibility of wormholes, hypothetical tunnels through space that could connect distant regions of the universe. If traversable wormholes exist, they may allow instant travel between distant points in space and even facilitate time travel. Closely related are closed time-like curves, CTCs, which are paths in spacetime that loop back on themselves, theoretically allowing an object to return to its past. Although the existence of CTCs is still speculative, they appear as solutions to the equations of general relativity under certain conditions, such as in the presence of rotating black holes or exotic matter with negative energy density. However, the concept of time travel is full of paradoxes and scientific challenges. For example, the grandfather paradox asks what would happen if a time traveler prevented his grandfather from meeting his grandmother, thereby preventing the time traveler's birth. Such paradoxes highlight the possible logical contradictions of changing the past. Additionally, the energy requirements and stability issues involved in creating and maintaining wormholes or CTCs are enormous. Theoretical models indicate that negative energy or exotic matter would be required to stabilize these structures, but such materials have not yet been definitively identified. Webb's ability to observe the early universe is central to our efforts to understand the nature of time and space. By capturing the light of the first stars and galaxies, Webb provides a glimpse into the infancy of the universe, providing critical information that can refine our models of cosmic evolution and the behavior of spacetime under extreme conditions. By observing distant galaxies, astronomers can look back in time because the light from those objects traveled billions of years to reach us. This time travel through observation allows scientists to reconstruct the history of the universe and understand the processes that influenced its evolution. Webb's advanced instruments will greatly contribute to the study of black holes, regions of space-time where gravity is so strong that even light cannot escape. Black holes are predicted to warp space-time to such an extent that they can form wormholes or closed time-like curves. By observing the surroundings of black holes, Webb can provide indirect evidence of these exotic structures and help scientists understand their properties. In particular, Webb's ability to detect infrared radiation is well suited to studying accretion disks and jets associated with supermassive black holes at the centers of galaxies. These observations can reveal the dynamics of matter and energy near the event horizons of black holes, shedding light on the nature of these enigmatic objects. One of Webb's most exciting missions is to identify and characterize exoplanets, planets that orbit stars outside our solar system. Webb's instruments can analyze the light that passes through the atmosphere of an exoplanet, looking for chemical signatures that could indicate life. The discovery of extraterrestrial life, even in microbial form, would profoundly affect our understanding of time and space. This indicates that life can arise in different environments throughout the universe, raising new questions about the origin and fate of life in space. Time travel has been a popular theme in literature and film for over 100 years. The novel The Time Machine by H.G. Wells, 1895, is one of the earliest and most influential works of fiction to explore the idea of time travel. In this story, a scientist invents a machine that allows him to travel back and forth in time, experience the distant future, and witness the ultimate fate of humanity. The Back to the Future film trilogy, directed by Robert Zemeckis, has become iconic for its imaginative and entertaining portrayal of time travel. The films follow the adventures of Marty McFly and Dr. Emmett Brown as they navigate the challenges and paradoxes of changing the past and the future. Although time travel remains speculative, its depiction in popular culture has inspired scientific research and technological innovation. Thought experiments and paradoxes presented in science fiction led physicists to investigate the theoretical basis of time travel and to investigate the feasibility of phenomena such as wormholes and closed time-like curves.
For example, physicist Kip Thorne, a leading expert on general relativity, has done extensive research on the possibility of traveling through wormholes. His work, along with other theoretical physicists, expanded our understanding of space-time and its properties. The concept of time travel raises deep philosophical questions about the nature of time itself. Is time a linear progression from past to present to future, or is it a more complex and malleable dimension? Theories of time such as presentism, the view that only the present exists, and externalism, the view that the past, present, and future exist at the same time, offer different perspectives on these questions. The possibility of time travel also challenges our understanding of causality and free will. If the future can affect the past, as certain interpretations of quantum mechanics suggest, traditional causality may have to be re-evaluated. Additionally, the ability to change the past can affect the concept of free will, raising questions about whether our actions are purposeful or whether we have the ability to change the course of events. Time travel also has serious ethical issues. If it were possible to travel back in time, should we try to change historical events? The potential consequences of changing the past are unpredictable and can have far-reaching and unexpected consequences. Moreover, the responsibility of holding such power would require careful consideration of the moral and ethical consequences of our actions. The possibilities of time travel also raise questions of equity and accessibility. Who would have the right or ability to travel through time? Is time travel regulated, and if so, by whom? These questions emphasize the need for a thoughtful and inclusive approach to the potential development and use of time travel technology. The James Webb Space Telescope and the concept of time travel represent two of the most exciting and ambitious frontiers in human research and exploration. While Webb is poised to revolutionize our understanding of the universe with its enhanced observational capabilities, the concept of time travel challenges our understanding of reality and the nature of time. By continuing to push the boundaries of science and technology, we can deepen our knowledge of space and explore the deep mysteries of existence.